Hello everyone. Today I'm just gonna record my class. The reason behind is I'm still in a new apartment. I just moved, and the internet is a big issue still. And so gonna record it in class and upload it, so that I'll finish whatever I finish today, which is going to be the entire chapter. That will be the syllabus for the exam next week. I'll also upload a practice exam, so that you guys can look at the practice exam and know what to expect for the main exam. The main exam would be next Monday, and next Monday it will be you have time from 6 p.m. Till about next day morning 6. Well, you can make it 10 p.m. To finish it and upload it. If you need extra time, you can email me and tell me the reason why, and I might give you the extra time. Um, it's all theory, so it shouldn't take you more than 2 hours to finish. So I'll be there online from 6 to 8, so that would be the major time for you guys to finish. Uh, I'll be online, so if you guys have any questions about any problems, I can or questions in the exam, I'll be there to answer it. So this is where I stopped. So the microscopic, when you start looking at the fatigue cracks under a microscope, uh, it is strongly controlled by the slip characteristics or the direction of the slip planes or the persistent slip planes, and also the size, microstructural size that we are looking at, and also the size of the load that you're applying. If the loads are high, uh, you will see certain slip planes, and then that's it, the crack would initiate and grow. But if the load is really low, you would see a lot of slip planes getting uh, connected at a lot of different places, and that's the major difference that you're going to see in terms of looking at it in microstructurally. Uh, so in ductile solids, you will see a lot of slip planes provided in a lot of different places, and then you will see localized deformation. So it's not that there is only one crack generated in the whole material, then that crack is the reason why failure happens. At the same time, there are thousands of cracks which are generated throughout the material. It's just that one crack becomes the major crack and how it grows towards failure. Doesn't mean that that's the only crack that happens. That's just the major crack, which was where the slip planes were. Um, the dislocations that was growing was maximum in that region. The other ones becomes non-dominant after a certain length. Uh, so intense localized deformations. Uh, that's the reason how when the plastic zone becomes bigger, there's a lot of localized deformation that happens, and that will generate your new crack that is growing from the plastic zone. Uh, so when the plastic tip or the crack tip and the crack size is a few grain diameter in size, uh, at that point, that whole crack would become cracked due to that single shear that is happening in that single plane. Uh, and this single slip mechanism leading to a zigzag crack path has been termed as the stage one crack growth. That's the one in which you have all the dislocations, all the slip planes and persistent slip planes are all created in one dominant region or dominant crack, created a dominant initial crack, and at that point is when you know that all the failures is going to happen in that plane of the material, but still the rate of which that uh, crack is growing is short. Uh, Stage one is seen in variety of different materials, mostly in all ferrous materials, in all aluminum alloys, all copper alloys, all materials that you know are going to be really ductile. You can see the effect of stage one crack growth in them for sure, and also you can see a definite divide between stage one and stage two in these materials. In terms of stage two, this is the same. This is the slow crack growth region or the controlled crack growth that is happens in the material, and this is after the major shear plane is decided in the material. There is a constant rate at which the crack grows at this point, and the stress intensity factor or the K value is a little higher. And the plastic zone that is grows in front of the crack tip, before it can grow even further, the plastic zone alone encompasses a few grains, because it becomes so bigger because of the way the crack grows at this point. The plastic zone in front of the crack tip is so big before it can grow even more. There is a duplex mechanism. That means the crack can is affected by two different things, and also the way the crack grows has a mode 1 crack path normal to the far field tensile strikes, which means that the crack is now growing perpendicularly to the direction of loading that you have. In single crystals, the transition from stage 1 to stage 2 is seen very clearly, where you just see that the stage one is going to be the formation of dislocation in the within the cell structure or grain structure, and then breakdown of creation of persistent slip bands for it to grow even more at the crack tip, and all those different things is what you see in a single crystal. Stage 2 crack is what is causing striations in most metals. So when you see striations after a fracture surface on a fracture surface after the failure happened, that's when you know that uh, the fractures happen, that striations happening, then you know that there is second stage 2 fatigue crack that happened in that material. The first time that they saw stage 2 crack or striations was around 1950s, and then that's the reason why till about 1950s there was not much of real good research in metals. Only during the World War II, most of the research in metals became was on full force, because everybody wanted to be better than the other person. Uh, so so that's the reason why in the 50s is when they started seeing all these all the results and all the journals on these came out after the World War II ended. That's when they started seeing these things differently, and people started understanding the work of different materials. And that's when, even if you take an aeroplane, the growth in the way commercial airplanes work went from 30 to 200, 300 people in a plane within a decade or two. And that all happened because they were started to seeing how fatigue works in these materials, and how important fatigue is to in make material characterization for any application that is there. Um, so striations are very very important to see. As I said, striations shall striations are just like how I have told this in class before. It's like looking at a tree and looking at the circles in a tree for the life. The amount of striation tells you whether the material is really ductile or had a lot of plastic deformation before failure, and all those things can be seen by looking at striations. Many polymers, which are also uh, engineering polymers also see have striations in them, because the way that they were designed are also designed also take a lot of fatigue loads and everything. So that's the reason why. Uh, the reasons why striations are developed in materials are because of the stress intensity factor that is applied. The alloy content, different kind of materials act different ways in the formation of alloying. Um, the environment plays a very very important role, and the way you can find out whether oxide is getting formed is when you see a fracture surface and you start seeing a cloudy image on the surface. That's when you know that there is some form of oxide that is generated on the surface. That oxide generated on the surface can just be because of the failure and the material being on environment. So first, they generally tell you after you finish the test, you take the fracture surface, blow air on the fracture surface, and clean the fracture surface, and then look at under the microscope. Uh, so these are the three steps of stages of of fatigue. So this is the stage one when you're gonna have a small crack initiated, but that is the major crack in that stress field or in that plane. So that's what is generated in one. So the amount of crack growth that you're gonna see is in nanometer level. So it's not easy to see in your or hundreds of nanometers. So it's going to be very very small, or sorry, hundreds of picometers. So it's 10 power minus 12, so 10 power minus 10 meters. So it's going to be a really really small when you see it. I can't even mention it, but when it goes beyond certain grains, that's when you know that's the major crack that is going to continue to failure. And then after that, it goes from picometers to about nanometers in your stage two, which is your Paris region, so where they have a constant rate at which the crack is growing, and it goes up to microns, a few microns per cycle, and then after that, this is the stage three is generally unpredictable. You cannot say whether it will go uh, in a particular rate or not. It depends so much on how the material is and the environment is. And generally, region B plus region 3 is only 10% of the life of the material. So in that, if you think about it, this would be 9%, and this would be just 1% of the life of the material, or even less. Most likely less than 1% of the life would be stage three, where you got just the crack is growing at a very high rate that failure can happen within a few cycles. So regimes of fatigue crack growth is what we're going to talk about. The Paris law, which is used in the stage two, uh, just gives you a constant or a slope where you can understand the rate at which the crack is growing in the material. Uh, the extreme values of delta K, um, both below the Paris region, which is in stage one or stage two, once there is extreme values of, then the rate at which the crack grows is going to be very very high. Um, for most engineering alloys, the way that you're going to see the three stages are just going to be the same. It's going to be like this. That's pretty much how it's going to go. Regime A, the average growth increments per cycle is very very small, and this is the place where you understand the stress intensity factor for the crack to initiate, and then the k delta k value after that is going to keep increasing. In stage 2, the rate at which it increases would be a constant rate, and in stage 3 is when it will be unpredictable. It depends on the environment and the rate at which the load is applied. It can fail within a cycle, it can fail in 10 cycles or 1,000 cycles. It depends completely on how the material works. um, and stage 3 is the point at which it can turn into a catastrophic failures pretty easily. So that's the reason why when they start looking at failure, fracture surfaces and all those things, they want to figure out the point at which they have to replace the part. Just because you see a small crack in the sample doesn't mean that you have to replace the part immediately, but you have to understand the size of the crack really well, and see whether the crack size is still way below what it has to be a critical crack length. And once it is even closer to the critical crack length, that's when you have to replace the part. If you don't, um, the point at which from which it's at this point it's like, let's say, oh good, it's still working, can turn into, oh shit, it failed pretty quick, and you would not know uh, how fast that is going to happen. So this is basically going to give you overall understanding of all three stages. In the first stage, the crack growth is going to be slow, and it's going to be like a serrated or rough, faceted region, where you're going to see, um, eh, when you look at it under a microscope, you're going to see the cracks and all those things, and everything is going to be has some facet to it. The crack closure, which we'll be talking later, the effects of crack closure would be maximum in terms of stage 1, where crack closure effect can improve the material properties or uh, increase the K1C value or K value in the material, depending on the conditions. Stage 1 is completely dependent on environmental, very dependent on load ratios applied on the microstructure of it, where major difference between 1 and 2. 2, no matter what microstructure, once the crack has reached a level where it's going to be steady crack growth that you're going to see in the material, there is not much of any effect of load ratios or the amount of load applied, and also the type of microstructure that you have, but there is going to be still a big effect on the environment. There's not going to be a chance that the environment is not going to be affecting it. So uh, So in the same thing, in an easier way to write it, in region A, microstructure is going to be affecting it. Mean stress is going to affect. Environment is going to affect. In region 2, there's little to no influence of microstructure, mean stress, or thickness. Variable influences of environment is still going to affect it. Stage 3, any small changes is going to make it fail faster or survive for a long period of time. So near threshold fatigue crack growth, this is when your fatigue crack growth is going to go faster, and understanding the fatigue thresholds is very very important, because once we know this value and the crack extension is still in microns on nanometer level per cycle, that's when you understand, okay, still we can use the part for application. And once it goes higher than that, that's when you know that you have to replace the part. So for example, if a fatigue crack growth were to occur in a rotor assembly at an insignificant rate of 3 nanometers Yeah, 3 nanometers per millimeter. Sorry, 3 picometer per cycle. Uh, so this means that the overall crack advance is of 30 millimeter during a lifespan of 10 million cycle or 10 part 10 cycles. So that's 10 part 10 cycles. Let me correct that. It's not 10 million. So that's 10 part 10 cycles, and that's how different for a rotor is. It has to go 30 millimeters for the failure to get happen, but you are at 3 picometers per cycle, and so basically you can get a whole different life. But although fatigue design is based on delta K, uh, be very very conservative design, but that conservation is needed for applications where you have turbine blades, turbine shaft, and all those applications where life is involved. You have to have a very conservative design to it. So in terms of conservation, the reason why you need conservative design is like the microstructure, the load ratio, environment, and the crack size changes with every time you use it. All these numbers are going to be different with an increased crack size from one step to the other. So these numbers are just keeps changing. It's like having a new problem every few months because of the rate at which the crack is growing. So you are understanding the life of the material at this from that point. So it is like a new problem every few weeks, and you have to understand how the material will work from that point to the future, and when you have to replace the part. Uh, so this is the effect of load ratio, and you can see that when you have a high load ratio, the curve is steeper than what you have at the low rate ratio, because in load ratio, the difference in which you're going to have a crack closure effect or anything that is happening in the material is not going to be higher, and the amount of load that you are applying, uh, the range, stress range might be almost same, but the way that you might be going through zero and all those different things can affect the way that the performance of K1C is going to be, and also the performance of the material can be. Uh, in terms of intermediate region of fatigue crack growth, uh, sorry, I don't know why I was talking, and my internet was in school was just running around. Uh, so this is basically Paris region, or the constant rate at which crack growth region. Uh, so in this way, the intermediate or Paris region. This is where even now to till date the research is going on extensively, so that they can extend the life of the material, or they extend the life of how when you can still use the material a little bit more than what they can use it right now. And this is as we said, doesn't affect much on based out of stresses applied, but it plays a very very important role, as it affects the rate at the only thing major thing that affects it is the environment. So there cannot be one single theory that they can successfully use to study the crack propagation for this material, because all the stress conditions depends on different places where you're going to use the same material, and So the same material that is being used in India would not be the right material or the right condition for a material that can be used in a Siberian region or even in Canada. So that's two different places where you're gonna be. So there's a lot of quantitative models which uses the Paris region to explain stuff, but it is all not the best ways, because just a small change in the environment or a small change in the conditions can change completely the performance of the material. So the best thing that you can do with certain models like based out of Paris region is going to be just comparative models where you're going to rank the materials based on different microstructures and say how much that microstructure is going to resist the crack growth. So basically, you take the same material, heat treat it in several different ways, and process it in several different ways, or make it in different ways, and see whether you're creating a different microstructure every time, and then do set of the same stress loads in the same condition, and then compare them. In this method, you cannot just do one test at one stress level either. You have to do multiple tests at same condition, and you have to compare them. And then by doing that, you will understand what kind of microstructure is going to help you understand crack growth better. And this is be directly in one condition, one environment. And you can do the same thing in lab in different environments and study the comparison of which microstructure would help you. But that doesn't completely prove the point that that microstructure would work the exact same way as the model said, but it will be the closest that you can get in understanding the resistance to crack growth that you can do by doing a model like that. Uh, so another thing is geometrical model to understand constant amplitude fatigue crack growth. Uh, so this is based on crack tip displacement. So you can have an extensometer, uh, which is, as I explained before, is as a strain gauge kinda, but an extensometer is like two blades connected to a sample, where one blade is movable and another blade is constant. So when the material moves, the movable blade moves along with the material, and then it gives you the strain that is happening in that between the two blades. The same thing can be done in terms of crack tip by having the CTOD extensometer, which is a crack tip opening displacement extensometer, where you just put this, it's spring loaded, and you put it between two notches, and once the sample moves, the what happens between the spring loaded system is it releases the energy because of the stress between the two springs, and that can give you the displacement that is happening every time you cycle it. And understanding that crack tip displacement uh, will explain the rate at which that displacement changes, can give you an understanding of how and when the material becomes turns from being a good material to oh shit material at that point. So it makes you understand a lot of different things. This is the only best experimental way you can do it. And the cracked up opening displacement is directly dependent on the stress intensity factor or the stress at which you're starting it. So the change in stress intensity factor is going to affect the uh, cracked up opening displacement, and so the true expectation of dA by dN, or the rate at which the crack grows, inversely proportional to E, is generally true for metallic. So it's inversely proportional to the elastic modulus of the material, the rate at which the crack grows in the material. So damage accumulation. So that was a geometrical model. Now let's look at a damage accumulation model. Uh, and according to this model, this was created or improved by two people called Koff and Manson. This was improved on Rice and Wehrmann's theory, and they proposed a damage accumulation model based on plasticity on a one discrete surface yielding in tensile, and understanding the existence of a slip ahead of the propagating crack, and understanding that plasticity that is created in front of it, or the plastic zone that is created in front of the crack tip, is the basis behind it. How they did it in Rice considered that deformations to history of a particular point in an elastically perfect plastic solid uh, engulfed, so has a big plastic zone to which the crack tip, from the crack tip that is there is a big plastic zone, and the plastic zone has to go bigger for it to break the barrier and for the crack to grow more. Uh, and this was happening again and again once the critical value of the size of the plastic zone is reached, and it's bigger than what it was before. And Whitman did the same thing, followed the same concept that Rice did, and conditions of all the non-propagating cracks that also plays another important role. So now we have one major crack, and how we can study the one major crack. What happens, and how does other cracks becomes non-propagating or non-dominant, and what decides which becomes a dominant crack and not a non-dominant crack, is something that is very difficult to um, practically prove, but it is but you can easily understand that the reason why this can decrease, the rate at which the propagation happens decreases or stops, is when you reduce the stress amplitude applied. So once you have a major stress amplitude, and then you have reduced the stress amplitude in the material, then all the crack propagation that you have in the material is arrested and doesn't grow anymore. um, The threshold value that can be regarded as the minimum possible threshold value below which no crack propagation can occur, irrespective of preceding load history on the uh, structure. So this number helps you understand that, okay, now I don't have any crack generated in the material, or it doesn't matter how much crack I have, doesn't matter how bad the material is. This threshold value is going to help me understand that if I apply a stress below this certain value, all the cracks that I have in the material is going to be a non-dominant, because the stress that is applied is not enough for any of these cracks to have enough energy for them to grow. The threshold value can be attributed to various competing aspects: the basic resistance of the material to the crack propagation, the compressive residual stresses that's there in the material, and the crack closure effect. So all these things can change the value of the K, that can affect the rate at which the crack grows or stop the rate at which the crack grows. But depending on all these numbers can be generated by doing a bunch of experimental data and creating a numerical model which tells you exactly at what stresses, below what stresses you would not see, no matter what the condition is, you wouldn't see any crack growing in the material. And these threshold values can be found for most materials, most common materials, you can find out these threshold values, and it is generally like one third of the yield value is taken as the threshold value. Generally, it is not true for all materials because changing in load ratio is going to affect it too. But it's if you don't have any data, you can assume that value to be true. Uh, so, what is the effect of mean stress on fatigue crack propagation? So, the mean load is going to affect the crack initiation in the material uh, and crack propagation in the material. So, if you have load ratio at the end cannot affect the way by which the material works, the growth or the graph by which both grows would be the same amount of change, except that it would have moved from one region to the other. Uh, Change in load ratio also has a little negligible influence on the rate at which the crack grows in the material. Uh, But when you have a fully reverse tension compression test, when you have -1 load ratio, um, the growth rate increases in the material because this is because of crack growth closure. Because in every cycle, you're going to go to zero and close the crack, and then open it again when you go in the positives. Uh, so the crack initiation threshold is dependent on the magnitude of stress ratio. The crack fatigue crack threshold is also defined by the amount of striations and ductile dimples that you can have in the material. Uh, so the threshold stress intensity factor depends on the maximum stress applied and the stress ratio applied in the material. And that's pretty much it in this chapter. This was a short 40 minutes class for sure. But this is the end of this chapter, and I'll start the next chapter on Wednesday. But remember, for your exam, it is only this 5 chapters that is there for your exam. Thank you.